All right. Hello, everyone. Thank you for joining. I know it's difficult on the third day in the morning. Some people, still finishing parties, so I appreciate that you came over. So my name is Michal Nosek. I'm enterprise architect at Percona. So basically, my role is to help organizations to shape their strategies related to, open source databases that Percona supports, be it MySQL, be it PostgreSQL, or MongoDB. Guide them, help them with our solutions and our services pretty much. And today I would like to talk about MySQL in the cloud and specifically about kind of two options. One of the options, two of them, that are getting pretty popular. Of course, database as a service and using database as a service in the public cloud is more like commodity these days, like most companies do that, or at least you know how to do that. But there is also like growing alternative that is basically running your database on Kubernetes with your application. So I want to kind of compare a little bit a couple of areas in this space for those two solutions to kind of give you, well, hopefully a bit understanding what is possible with running database on Kubernetes, in the context of public cloud, in the most cases. So, agenda is actually pretty simple. I would like to set the stage with more like what I mean by cloud native applications and what is the role of Kubernetes in that, because I think that the definition of cloud native application is really not that clear. I have trouble myself, defining that really well. We will have a look at the options to run MySQL from the categories that I mentioned, and also have a bit closer look at the specific solutions because we can't compare everything on such a session. So looking at Google Cloud SQL MySQL and Kubernetes running MySQL with Percona Kubernetes Operator. In the description of the talk, you will see Percona distribution for MySQL Kubernetes Operator, like very long name of Percona product. Since I submitted that, the product name changed, so now it's Percona Operator for MySQL. So it's kind of really simpler than that, and I will try to use that name, but if I don't, it's because I'm so used to the previous naming, but I mean the same thing there. Before I go to actually, the later part of the presentation, I would like to ask you a couple of questions. So, who runs some applications on Kubernetes? Okay. So, don't be shy. There's nothing bad about that. Who runs MySQL on Kubernetes already? Okay, great. So the follow-up question is kind of, I'm a bit afraid always, like who thinks that running MySQL on Kubernetes is a terrible idea or the best idea I can ever have? And really? Okay, that's good. I really count on honesty, so that's totally fair, right? It's still not that much, percentage-wise that I would think, because I've been doing some presentations as Percona in a couple of cities in Europe, and it's interesting to see how in different places they actually look at Kubernetes. So, for example, in Stockholm, almost nobody raised their hand, but in Copenhagen, for some reason, they were like, it's a terrible idea. And there was like more than 50% saying, we tried, we failed, or, how dare you even, talking about that. But okay, thank you for that. So looking at cloud native applications, of course, cloud native application is a lot more than just signing up with public cloud provider, spinning up some virtual machine, and then putting your application there, because it really affects entire design, architecture, and process of actually delivering and operating applications. So the impact of choosing to build cloud native application is much bigger than just where you run your application. But as I said, I'm not that good at definitions myself, and I really believe that definitions are the kind of second most difficult thing in the IT world, right after software, like naming conventions in software development, right? So you name classes and stuff or variables. It's first thing that is the most difficult. The second is, getting right definition of some technology or some approach, because everyone has a different opinion. So I'm looking at, some industry experts. So Pivotal, which is now VMware, They say that cloud native is an approach to building and running applications that fully exploit the advantages of cloud computing model. It's not very precise, but what that means is that basically you would like your application to be scalable, to be kind of flexible, to scale to the workload that you have, to utilize cloud computing in a cost-efficient way, and many other things that are related to that. The Cloud Native Computing Foundation definition, I like it much more because it's more precise. They say that cloud native computing is about open source software. That's kind of first and the foremost. Then it's of course containerized. So you want to have it packaged in the containers so you can run these containers on different infrastructure without actually re-architecturing. It's dynamically orchestrated. So these days big applications have multiple services, hundreds or thousands of containers. So there needs to be something that puts some order into that mess with all these containers, because it's easy to break things into pieces, but then to keep order, put order into those pieces is kind of much more difficult way. And that's why we have a concept of container orchestration. And of course, microservice oriented, because in order to get all those benefits of cloud computing, you need to have the like smaller pieces that you actually run, so you can scale them independently. You can develop them independently, release independently, and so forth and so forth. So like putting all these things together, I try to simplify that into like a couple of words. Microservices, so smaller pieces rather than big monoliths, running on Kubernetes, because let's face facts, like container orchestration these days is mostly Kubernetes, except some edge cases maybe. We have different Kubernetes distributions, but it's still Kubernetes. They are cloud-based, but not only public cloud-based, but also private cloud-based. Especially larger organizations not only kind of use managed Kubernetes clusters, but they, for example, deploy OpenShift or some other solutions that are also basically Kubernetes, and they create also their private clouds and they consume it infrastructure this way. From the database perspective, it's important that in this context, in most cases, we will be looking at the data store per service. So some database per service rather than big database as a monolith that takes care of everything. And the reasons for that are multiple. Like, you want to use right tool for a job. So there is a service that better fits document model, so you use that. Or maybe you have developers skilled more in one database in one team and another RDBMS in another team. So you want to have this freedom and flexibility, also choosing technology, scaling that. And with all bells and whistles that every technology comes with, you want to be able to use that. So if you put that on some form of diagram, this kind of sample cloud native application, you will see that you have some services that are running basically containers. There may be multiple containers per pod in Kubernetes. And for those of you who are not familiar with Kubernetes, pod is kind of the smallest piece that you can actually move and scale and describe in Kubernetes. A couple of containers may form one pod, and then you have multiple pods to scale specific service-specific applications. You'll have multiple such services. There will be some load balancer in front of those services, some API gateway or the request flow. Another service that exposes that API gateway, some external load balancer in the cloud, together with ingress and egress controller in Kubernetes, in order to make it public to users or whoever consumes the API or the application. And typically these applications also use tons of different cloud provided services, so cloud authentication, authorization services, so monitoring, logs, and so forth, and all this for you to be able to just focus on the application and the code, right? And if you're not familiar with Kubernetes, we probably don't have time to look into details of Kubernetes, but the idea is that you have some form of control plane, so all the elements that actually make it kind of possible to this complex machine to work with the API, with the APIs that you can use to also deploy things and control things, with some schedulers, controller manager, etcd key value store to keep the state there, And kind of other side of Kubernetes is worker nodes, right? So I just want to kind of explain this concept that worker nodes is basically pool of resources, servers that join the cluster, and then control plane can basically schedule containers in form of pods on these worker nodes, and you may add as you need. You may have multiple pods in these worker nodes. And there's, of course, a couple of Kubernetes components on each worker node and the container runtime. But in general, this is where your workloads actually are run and where they happen. So what are the options in such a context and cloud-native application? I mean, first of all, natural choice is, hey, we are in a public cloud, let's use database as a service. So for example, RDS Aurora, or something else. And then you kind of have your application in Kubernetes cluster, cloud services, you consume database as a service. Pretty easy to set up. We'll also have a look, how it works and differences a bit later. And the second idea that I kind of want to compare this approach to is running your database in Kubernetes with your application. So kind of treat your database in a similar way as your application, and kind of try to manage it in a similar way, running in the same cluster. It gives you multiple benefits because then you don't think about database as a specific service. It's kind of yet another application that you run in your Kubernetes cluster. So you can take benefit of, for example, being able to move database and application in the same way between cloud providers or between different Kubernetes cluster, which is also useful in the hybrid cloud models or multi-cloud models in general. So we're talking database as a service or Kubernetes with application. Those are the two things that we're going to have a look at today. And what are the database as a service options? I kind of try to divide them into two, so kind of cloud vendor provided. So AWS has its own, Google Cloud has its own, Azure has its own. You'll find also MySQL in Oracle Cloud in form of database as a service. It's not that easy to find kind of cloud independent in the MySQL world. The one I know is Avon, so it runs your workloads on AWS or Azure or Google Cloud, but it is not owned by any cloud provider, so you're kind of more independent. And what is the value proposition of database as a service? I think that's not a surprise. You don't care about infrastructure, and it's kind of easy because you want to deploy, so day one operations, that's click of a button, and then you want to upgrade, you want to take care about high availability, you want to take care actually whatever is in the scope of the day two operations. This is taken care of for you. At least you count on that. That is easy. With Kubernetes though, there are like a couple more benefits, right? So first of all, Kubernetes abstracts underlying infrastructure. That means that, as I said before, you can theoretically move the workload from one Kubernetes cluster to another Kubernetes cluster, and you should not really face any problems. Again, at least in theory, because, for example, underlying infrastructure performance may differ. The storage that you have available, any other thing. There's no vendor lock-in, because essentially, you can run Kubernetes everywhere, so it's portable, as I said. In many cases, it's cost-efficient. Have a closer look on that later, but the thing I want to point here is, and it's kind of paradox of Kubernetes, because Kubernetes is supposed to make things easier when it comes to databases. That's not really the case. It's rather complex task. Even though Kubernetes kind of introduces new concept, it's much easier than it was in the early days of Kubernetes. It is still not that straightforward. So you need to take care of different things still. It's not just you take your database, pack it in the container, and that's it, right? It's not that easy because databases, not only MySQL, are stateful applications. So you can't just let Kubernetes move the pods around and kill it whenever it wants, or upgrade them randomly and these types of things. So you need to take care about stats. For maybe primary and replicas separately, about setting up replication and high availability, and what storage to use. Should I use network attached storage with persistent volume claims, or maybe should I use local disk that are available on my hosts? How to expose the traffic, load balancing, be it HAProxy or proxy SQL or something else, configuration, monitoring, backups, updates, and the list goes on, and they probably spent 13 seconds to put those 13 points. It is probably longer in practice. So the point is, there are so many components. If you have this application container that runs web server, and you just want to scale it, you just say, hey, here's my image. You mount Kubernetes secrets, environment variables, and you can have hundreds of containers, or tomorrow one container, and play around with that. It's pretty easy. With databases, it is not. There is much more to that. So what is Kubernetes Operator? In kind of simple word, because Kubernetes Operator is like a general concept. It's not related to MySQL. It's not related to Percona extensions. This is kind of framework of building applications that actually help to run other applications, because database in this context is also application. So operator is, in terms of Percona operators, is a bunch of Go code. So you basically will take container image with the operator, and you will run this operator as any other application in your Kubernetes cluster. It will just be run as an application. The second important part of the operator is custom resource definition. And custom resource definition is the Kubernetes API extension. So instead of using and operating with like basic Kubernetes primitives, as I mentioned, pods, deployments, replica sets, secrets, and so forth, you can kind of teach Kubernetes with custom resource definition that there is something like cluster as a primitive in Kubernetes. So you can talk to Kubernetes in kind of these terms, not about all the components. And then how it works is that this operator application basically pulls the Kubernetes API continuously in a loop, looking for custom resources that are, according to the custom resource definitions that operator is kind of interested in, right? MySQL operator will be interested in this specific API, for example. And then whenever operator sees the actual current state of the cluster or state of the applications that it's kind of taking care of is different than what is in the Kubernetes control plane with the definition, it will start taking actions in order to, remove the delta between those two states. So for example, if you tell Kubernetes, hey, there needs to be resource that is called MySQL cluster, and it should have five replicas, operator will see, oh, I don't have this cluster, so let's start making it, and it will deploy all the components that are required for that. So basically, operator provisions this basic Kubernetes primitives and all database components and configurations in the database context. So the general idea is that it simplifies. So the complexity should be hidden from you. You don't care how the traffic is exposed. You don't care how the replication is implemented, and many other things. So from the someone who uses the database cluster perspective, it should be more like, hey, I need MySQL, more like as a service, rather than, okay, how do I deploy HAProxy and make sure that I configure that, or what type of high availability solution should I use? So you're just talking to a service. So basically, operator aim is to solve for you or give you this it's easy part that you count on when you consume something as a service. So automate deployments and automate typical database administrator tasks. And what are the operators for MySQL available on the market? You will see Oracle with another try of building MySQL operator. They already tried a couple of years ago, but then they abandoned the project. Right now, there is a new operator project from Oracle. There is KubeDB, PressLabs operator, and for sure Percona operator for MySQL that I would like to focus. And operators in general can be divided into categories or categorized with the levels. This is something that comes from Red Hat that kind of aims to categorize operators. So you already know, if you look at some operator, what capabilities to expect, right? And this is anything on level 1 from like that operator just helps you to do basic installation of some software, or to level 5 that is kind of, holy grail or the ultimate goal of our operator makers to make an autopilot for some application. And that includes things like automatic scaling, but also ideally automatic configuration tuning and workload tuning based on what is happening. Of course, I wouldn't say that any operator is there yet. This is more like where all operators would like to be, so be aware. But if you, that's the try to categorize them and kind of give like simple description of what specific operator should be capable of in the world where, let's say in the future, everyone will use operators for different applications to simplify their lives. But my point here is that you should look at the operator as a kind of autopilot with a bit better or worse capabilities, pretty much, right? Okay, so let's have a look at a couple of areas of Google Cloud SQL MySQL and Percona Operator for MySQL. So I picked 8 areas that I tried to compare a bit, starting from architecture, how you actually deploy it, how you connect to it from cloud native application, what is the high availability solution there, what is disaster recovery and what are disaster recovery options, how do you update or upgrade such a cluster, how do you scale it, and how it affects or how the costs of both solutions actually look like, right? So this is what I tried to cover today. When it comes to architecture, for those of you who are not familiar with Google Cloud SQL, for my, I think that RDS is pretty similar. It's maybe a bit too light here, so sorry for that. But in general, it's pretty simple. Like you will have primary instance that runs on some virtual machine in Google Cloud, and you will have some standby. And this standby does not run database process continuously. It is placed in another zone, and they will use regional disk. Regional disk means it's actually disk that is replicated in multiple zones. So when the primary instance writes something, the database writes something to the disk, it will be actually written to 2 disks in 2 zones or 2 storage nodes, pretty much. And then, of course, high availability we'll have a look later, but you can suspect that standby can take over with this disk. Important, the IP address doesn't change, so you can just look at this as your database that you'll use. And of course, you can deploy replicas, multiple replicas. They will use standard asynchronous replication in order to scale reads and maybe put data in the different regions as well. When it comes to the architecture that is deployed with Percona MySQL Operator, it is using basically Percona XtraDB cluster as a high availability solution. So by default, you will have at least 3 nodes in order to guarantee high availability. And you may have, of course, more nodes. And it will also deploy for you the proxy layer or load balancing layer front. And you basically have 2 options here. One option is HA proxy, which will be layer 4 proxy, right? You probably are familiar with HA proxy, can be used for MySQL as well, in order to load balance between the nodes. And it will also deploy services in Kubernetes for you. So the endpoints that you can use in order to access your cluster that actually hide complexity of using a cluster, so you don't need to think about what happens after failover or things like that. So one of the services that you will have is read-write service, and it will actually go to HA proxy layer, and then this HA proxy will redirect all the traffic to first available node in the cluster. Theoretically, in Percona XtraDB cluster, you may write to all the nodes in the cluster because it's a multi-master solution. However, in practice, it's very rare that there is a workload that really benefits from that in terms of performance. So it's better to look at XtraDB cluster as a high availability solution, not the way to scale writes. In most workloads, it's better to write to a single node, and this is what Operator does for you normally. And then there is also a second service that is read-only service that will use remaining nodes and load balance read-only traffic between those nodes. The second the second option that you can choose when you deploy operator is to deploy more like smart proxy, which is proxy SQL. Probably heard about it or use that, which is layer 7 proxy, which actually understands MySQL protocol, and you can do much more advanced traffic routing with specific, for example, queries that you will redirect to specific nodes and so forth. But by default, it would be HA proxy SQL as an option. And you can also see that there is operator running that overlooks entire cluster. It's worth mentioning that one operator can virtually manage unlimited number of clusters. So there's not much resources that operator needs. It is enough to have just one. How do we deploy it? I think with CloudSQL, it's not rocket science. You go to the user interface, or you use API, or some Terraform providers that are out there. It's easy. We're not going to focus on that. With the operator in the Kubernetes cluster, you actually need to do a couple of steps. Of course, a prerequisite is that you have your Kubernetes cluster, that you have your API to Kubernetes configured, so you can use kubectl command line tool, that you have all required permissions to deploy, to create custom resource definitions and deploy applications in Kubernetes. You also need a namespace in Kubernetes. Then, as I said, Kubernetes is basically a bunch of the Go code and a bunch of YAML files. Operator is that. So you can clone the operator from GitHub. And there you also have this all you need to deploy into the cluster. So you clone it from GitHub, you basically deploy the operator file, and then what you expect is that the application is running. That's kind of first setup step, so you're then ready to move on and deploy your specific clusters. Now, if you want to create cluster, we also need to think about users. So you rely on default passwords that, so if you don't have a secret that contains passwords for your cluster, operator will generate secrets for you. But you can also take control over that and define your passwords for administrative users on your own through the secret. And there are multiple users, probably difficult to read, but for example, root user for MySQL, or a specific user that is going to be used by backup, or user for monitoring solution, or the user for the operator specifically, or the user for replication. The users that are like typically needed to for MySQL cluster to be running. And it's important that operator only manages administrative users, right? So it does not manage application users for you in any way. That's totally out of the scope of the operator, at least currently. Could be potentially implemented. But there are operators that do that, but our operator takes care about only administrative users. So you get the secret that you have a template, you put your password there because you don't want to use default passwords, and then you can go to configuring your actual cluster. So here you will see kind of simplified custom resource YAML file, which is basically the to describe your MySQL cluster that you need. So that's the entire idea. In the same way as you describe your application deployments in Kubernetes, you can describe your MySQL cluster. So you'll see a couple of things. First of all, that you see here, the kind and the API version. You can use that because you deployed custom resource definition, because custom resource definition is there with operators, so you can talk to Kubernetes in terms of Percona DB cluster instead of deployment pods and so forth. You'll have a name of the cluster, the reference to the secret, so from where the administrative users' passwords are coming from, the version that you want to use, and then the section that says, hey, I want a 3-node cluster, and each node will have 1 GB of memory request and 600 milli-CPUs, pretty small cluster, right? In usage, and then each node should have also 6 GB of the default Google Cloud provided storage. And then you decide, okay, I use HA proxy, so you just say you enable that to have HA proxy in highly available mode. 3 of those, and some resources on the HA proxy as well. Of course, you can configure many more things, like for example, enable integration with the Percona monitoring and management. That's super simple. You just need to say, hey, PMM enabled through, and basically put the server host and also some credentials that I don't show here. And you have your monitoring done, right? So, and that's related also to backups and many other things. But the idea is you take this declarative approach to describe your infrastructure, to describe your cluster, you deploy it on Kubernetes, and an operator, oh, somebody wants a new cluster, so I start preparing all the things out there. So you deploy the cluster, and when you check the resources that it actually deployed, you will see that you have multiple HA proxy pods with respective containers, that you have 3 nodes of the cluster, and then you still have your operators running. Additionally to that, you will see multiple services, and the most important ones are cluster 1 HA proxy. Cluster 1 is the name of our cluster. HA proxy means it's read-write service, so that goes always to the same node, and replicas its load balancing across remaining nodes there. How do you connect to this type of from cloud native application? Well, yeah, some people say, like, what do you mean, how do you connect? Like, you either use some function string depending on the driver you use, or you put the parameters of your connection and that's it. But it's not that easy. And for example, in CloudSQL, the recommended, you can either use private IP from Google Cloud, but the recommended way is to use Google Cloud Auth proxy to connect to your database as a service. Google Cloud Auth proxy is like Google provided tool that takes care first and foremost of authorization and authentication with Google Cloud primitives. So instead of using username and password, you can basically use your Cloud IAM roles and service accounts in order to provide access and manage permissions to the specific cluster. And you don't really need to put effort kind of on yourself or onto your application, and it basically simplifies that aspect. On top of that, it provides out-of-the-box security. So your connections will be secured, your application will connect over localhost to the proxy, and kind of the rest is always secured and encrypted out of the box. So you also don't need to solve that problem or challenge yourself. And the recommended way to deploy CloudSQL Auth proxy is as a sidecar container. So as I mentioned, so our application runs in pods and in one or more containers. And if you have your application and your application container, you can then deploy container on the side that will run this CloudSQL Auth proxy, and the application will just connect over localhost, and the rest is happening from Cloud Auth proxy. It also prevents the traffic to be exposed even internally, as I said. But it does not provide, for example, connection pooling. So if you need that for the larger scale, some separate layer is also needed. How do you set up that? I don't expect you to read the details of this, but I just kind of want to let you know how it works. So in Google Cloud, you have Google service accounts where you assign actually privileges to manage permissions. Kubernetes, on the other hand, has another concept, well, also service accounts, but these service accounts within Kubernetes cluster are separate from Google Cloud service accounts. So you need to create your service account in Kubernetes for your application, and then through the Google API, you basically bind Google service account with service account. So you need to match in order for Google Cloud to be able to recognize your workload from your specific service account in the other cloud services and decide if you have access, if you're authorized to do something or not. So you can do that through a couple of commands to bind Kubernetes service account and Google service account within Google Cloud. And then as the next step, you basically add a sidecar container to your application. So what I mentioned, your application, your container will run with specific service account, Kubernetes service account. Then additionally to your application container, whatever is that you run in Kubernetes, you will also define CloudSQL proxy sidecar container that, as you can see, uses the proxy. And then you don't really need to specify username or password or anything. You just say, hey, here's my instance that is within my VPC I want to connect. That's it. And then all the rest doesn't matter. You're connected. So that's pretty simple and convenient. Moving back to Operator, we deployed our passwords in a secret. So we either remember our passwords or we can retrieve them from a secret because they are there. They're just base64 decoded. So it's pretty easy. And then we need to create a user for our cluster. We need to create a user for our application that is going to use our Operator deployed cluster. So we can connect, for example, deploying a temporary container with MySQL client, as I presented here, and I'm connecting with the root user in order to create some user that will be later on used by the application. Once you have that, you need to create another secret that will actually keep the user that you created in MySQL for your application, right? So you create a secret, and let's say that you define a couple of keys there, like username, password, and you can also put your read-write host and read-only host in order to have everything in one place. Once you have that, you can mount the secret to your application, so to the specific application container. So the fields from the secret can be used and utilized within your container as environment variable. Okay? So this is Kubernetes concept, but that would be the step required in order to connect to the cluster. Moving on, I just have a look at the time. How the high availability is basically achieved in those setups. So for Google Cloud SQL, for high availability, you have like standby node that is, as I said, not running MySQL process, and then you have also some read replica. They use original disks. When the primary fails, basically, it's automatic. The failover is automatically initiated. However, you need to keep in mind that how the failover works is that there is a heartbeat message written to some central place in Google Cloud, and when there is no heartbeat for 60 seconds, only then failover will be initiated. So you need to keep in mind that in the best case, detection of the failure will happen in 60 seconds. Only detection, and failover can take more because MySQL process needs to be started and maybe some redo log replied. So depends on your workload. It may take a lot of time. If you look at the documentation of Google Cloud, they will say it's less than 3 minutes. If you look at the practice, it can be more or even much more because how it's basically set up. Okay. So basically, I just wanted to present how it's actually moved to another zone. With Percona Operator for MySQL, the high availability is achieved through Percona XtraDB cluster. Anyone uses XtraDB cluster or recognizes? Okay, good. Well, cluster is high availability solution built of Galera replication. But this is basically a synchronous, or some people would say virtually synchronous replication solution, meaning multi-master solution, meaning you can write to any node of the cluster, and then the transaction is going to be certified on all the other nodes. And once it's committed, it will be committed on all the nodes. So it basically works like this certification process is synchronous. So all the nodes need to agree for the specific transaction to happen. They typically work pretty well. They work pretty closely. You also need to consider latency in that, because the transaction can happen only as fast as you can reach other nodes in order to finish certification process. But you can achieve like very good high availability with Percona XtraDB cluster. I would say that typically with the proper setup, it can go as much as to 4.5 nines, which will be better than Google Cloud SQL in that setup. But it's a different solution. So one thing is a high availability on the MySQL cluster level. Another thing is high availability on the HA proxy level, because you want to avoid single point of failure. But Kubernetes takes care of this, as it treats HA proxy as just any other replication. And you don't need to really think how to move application and reconnect, because HA proxy is reconfigured basically by the operator when the failover happens or you lose one of the nodes, it will move the traffic accordingly. So this is transparent to you as the user of the application. Important thing I want to mention is the Kubernetes anti-affinity concept, which is basically a mechanism that helps you to force specific deployment, in our case MySQL cluster, to be deployed either on the separate hosts, the Kubernetes, separate worker nodes, or even in the separate availability zones. So by default, the cluster that you deploy with the operator will place all the members of the cluster on the separate worker nodes, right? So that way, if you lose a single worker node, you're not going to lose your cluster. You can also change that with the specific topology key in your cluster definition in order to enforce placement of the pods of the same cluster on in multiple zones if you need this type of high availability. For your MySQL. All right. Looking at disaster recovery, what I mean by disaster recovery is what happens when you lose entire data center. And there is no simple and good answer for that in Google Cloud SQL, unfortunately, because there is a lot of manual work actually to do this failover in such a scenario. All you can do, or you can do, is basically having a regional replica, which is some asynchronous replica in another region. However, when you lose your primary region, you need to manually promote this replica to be the main, to be a primary. And the problem is with that if you promote it, and some applications will use that, but then for example, first region that previously failed comes back, you may have two databases that you're writing to suddenly independent, and you need to take care of this situation, totally on your own. So you need to move the workload, use another IP address, rebuild your replicas, and the procedure needs to be repeated if you want to fail back when the region goes back. Operator actually simplifies that thing a bit, because there is a concept that was introduced actually by MySQL a couple of versions ago of replication channels and automatic replication failover slot, if I'm not mistaken how it's named. The idea is that you have two clusters. One cluster that is running as your main cluster, and another cluster that is continuously replicating from your primary cluster through asynchronous replication. Both clusters can be either on Kubernetes, or one of them may be outside of Kubernetes. So this is also useful for migration from outside of Kubernetes to Kubernetes deployed MySQL. All you have to do is to set up, like, on one side, on the source, so your main cluster, you need to set up replication channel and tell operator that this is your source cluster. That's just the first step. The second step is that you need to expose all cluster members to make it possible to replicate from them. So if it's in another data center, it typically means it needs to be opened to public internet. So in this case, for example, you can expose with load balancer, and in Google Cloud, it will give you external load balancer. So essentially your pods, all the members of your cluster, will be available with different IPs in the public internet, right? And you can also use DNS there. But the point is, you need to expose them somehow. So they need to be reachable from the other side, from the replicas. To replicas, you need to tell operator where do you want to replicate from. So basically, you set up replication channel. You say that it's not source, this is not source, this is replica, and you specify addresses of the sources. So basically, your primary cluster, right? That means that if we expose them under pxc1.source.percona.com and pxc2.source.percona.com, we need to put that in configuration so we can replicate. And the same applies if you want to replicate from some existing non-Kubernetes MySQL into Kubernetes MySQL. That can be used as well. On the failover, it's pretty simple. You just lose your cluster where you're replicating from. You just say now it is source, or you remove that configuration, and you can continue using cluster basically as a primary. I want to a look at the time. We started later, if anything, so just a couple of more minutes. I will skip maybe updates and have a word on the scalability. So scalability, when it comes to the databases, of course, we will have a couple of concepts. The easier is vertical scaling, where you will add more resources. Horizontal, you will add more nodes. Sharding is out of scope for the operator. But if you want more resources to your cluster, you basically need to change your custom resource parameters, and you say, hey, now I want double memory. And then when you deploy it, the operator in Kubernetes restart each member of the replica set, of the cluster, in order to give them more resources, and they will do this one by one, so you don't lose too many members at the same time. With horizontal scaling, you may just go and say, hey, I don't need 3 replicas, now I need 5 members of my cluster. And then it will start adding them, it will initiate a clone process, and it will also basically drive it to the moment where the new node joins the cluster. There is also a concept of auto-scaling in Kubernetes, which is very interesting in general when it comes to any workloads, and especially databases, because autoscalers in Kubernetes, they basically analyze the usage trends of the or resource utility of your deployments, and based on that, they can react. Basically, they can assign resources, add more resources, or add more replicas to your Kubernetes deployments. It is not that easy with databases. However, you can use already vertical pod autoscaler with the operator. If you target with vertical pod autoscaler specific deployment that is responsible for your cluster, it can actually add more resources. And for example, specific threshold is, it goes, the CPU usage goes over a specific threshold for a longer period of time. So the trend is you need more. So the autoscaler will actually assign more resources. However, keep in mind that this is not to react to like sudden spikes in your traffic. Adding resources requires restart of the cluster members, and it cannot just happen all the time. So this is more like to cope with trends rather than with sudden traffic, which is actually true with also all the kind of serverless invention databases, Aurora serverless. You also can't really count on this, that it will add resources in a second to cope with the load spike. The horizontal autoscaler cannot be yet used with the operator, but hopefully that will come a bit later. So it will be also possible to change the number of cluster members dynamically based on that. And the very last thing, cost. Cloud is expensive. Some people say it's cheap, but it's actually expensive all the time. So I tried to come up with some very simple calculation to show you difference in the pricing and why it's interesting to look at Kubernetes as a platform or way to run your databases. So let's say that we have 6 microservices that require MySQL. Very simplistic. Each microservice will need 3 database nodes per database environment, right? So 6 microservices, each needs 3 MySQL, and each node needs 16 cores and 64 gigs of RAM and 500 gigabytes of SSD storage. I skipped all the small variables like which region I use that, or what is the cost of the traffic or backups, because this would be similar in both solutions. But we're looking at the pure resources. So if you look at Google Cloud, you need 6 primaries in highly available mode and 12 replicas. The total that you're going to get from that with the standard instances is around $250,000 for this kind of setup. 6 microservices with this type of MySQL clusters. On the other hand, if you look at where you can run this or fit this workload on Kubernetes, doing some math, we need 288 cores to do that. That means if you decide to run all of those clusters on 3 worker nodes, we'll need 6 cores per node and 384 gigabytes of RAM and 3,000 gigabytes of storage. You do the math, and you will see that the bill for this type of setup, the same type of resource, be roughly half of this, right? So of course there are like many more things to consider. You know, the performance of the extra DB cluster comparing to asynchronous replication will be probably different depending on the workload. You will have some other things that you need to run, like connection pooling or load balancers. But with this difference, it's at least worth to look at this as an alternative, especially if you have larger scale, because yeah, even if you need to, you know, give up or trade some convenience for a specific money, it typically makes sense. And as a summary, to kind of, you know, repeat that, I think that running MySQL on Kubernetes can be interesting alternative, assuming you use some operator. But of course, Kubernetes knowledge is required. So whatever you just think about doing, rather start with your applications and then look at the databases, because it's still more difficult. Evaluate different operators. The ecosystem is rich, and these projects evolve really, really quickly. And also, from Percona, the new version of the operator with more options to deploy your clusters with either asynchronous replication or group replication, that is native MySQL solution, clustering solution, is also coming. There's also already some code available on GitHub. And that's pretty much all I wanted to share with you today. Thank you. Any questions still? No questions. Some guys from Percona came. You guys have questions? Better not. Here will be difficult ones.
No, you mentioned that only vertical auto scale is there. And why does vertical require a restart of the entire cluster? Isn't that resource based?
Yeah, it's Kubernetes limitation.
Okay.
So you can't dynamically add resources without restarting a pod, pretty much.
But you can do that the same way that you would just make a regular change, right? That only do one pod at a time, or in that instance it does them all at once?
No. It will do one pod at a time, because the allocation is per pod, so it can just do one at a time. And while it joins and it's healthy, it will start with another.
Okay, so you're more saying that the performance hit is because at your peak need, you've now taken a cluster out to then.
That's one thing. And second thing is that it takes time. So it's already gone when you have the new resources, right? Just too late. No.